Now we're going to talk about heat transfer mechanisms. We've already talked about some ways you can give energy to an ideal gas, but this is more general, how you can give energy, specifically heat energy, to anything, a piece of metal, a gas, or anything. The first mechanism is called conduction. That's simply transport of thermal energy through a material when colliding particles exchange kinetic energy through direct contact. Molecules running into other molecules, or electrons running into other electrons or molecules. The next method is convection. This is the transport of thermal energy by bulk movement of a fluid. A fluid is a liquid or a gas. Both of those are considered fluids. And when a bunch of fluid moves, and that's got different temperature than some other fluid, you can actually heat things or cool things. That's how heating your house works for many people. The last mechanism for heat transfer is radiation. This is transport of thermal energy when vibrating electrons, molecules, or other charged objects release energy in the form of electromagnetic radiation. Let's first talk about conduction. Conduction is the transfer of thermal energy through a material by transfer of kinetic energy of molecules and their electrons to other molecules and electrons with which they collide. This happens in any substance. Whenever part of it is hot, those molecules will move fast and crash into other molecules in the substance, making them move faster. Here's a heat conduction animation from Mr. George's YouTube channel. That flame is just a bunch of burning gases which have fast-moving molecules. They are contacting the molecules of this metal, which is shown as a crystal. And you can see that the kinetic energy moves from the fast-moving molecules towards the slow-moving molecules. And you can see the temperature, which is represented by the color, red being hot and blue being cold, moves from hot temperature to cold temperature. So this is a model of conduction, where fast-moving molecules crash into slow-moving molecules, moving thermal energy from hot to cold. The fact that good thermal conductors like metals are often good electrical conductors as well demonstrates that in thermal conduction, some kinetic energy must be carried by what particle? Well, what particle can move easily in good electrical conductors? That's electrons. Electrons can also carry thermal energy. They're just moving fast and can run into other molecules and electrons. Here's a molecule, boom. They have that's what conduction is. When you take two materials, put them next to each other, and the molecules, when they're next to each other, the molecules hit each other and transfers thermal energy from one to the other. So, and it is the electrons as well. It's not only the atoms, but the electrons can be moving around and bounce and hit other electrons. So it's the transmission of, in fact, translational kinetic energy, but for ideal gases, but for any object that's kinetic energy. Now, what we have to be able to do is calculate the flow of heat through a slab of material. In other words, that's called the rate of heat conduction. The flow rate of heat, or H, is the rate of energy transfer by conduction. It's how quickly, in joules per second or watts, energy transfers out of one object and into another. You got to understand the effects of these variables. The changes in thickness or area of the slab, or the temperature difference between the two faces of the slab. So there's three things that affect it. The length or thickness of the slab, the area of the slab, the cross-sectional area or area in contact, and the temperature difference. So now the rate of heat transfer, a lot of times, and our textbook, I believe, does use the letter H for this. You could use a different letter. Rate of heat transfer, it's a rate. It's in joules per second, or what is a joule per second? It's a watt. What is the other symbol that many textbooks actually do use for this? W would be work. That's not what this is. This is the rate of energy transfer. P, capital P for power. So some books use capital P for power instead of H. So it is a rate of energy transfer. And the rate that thermal energy is conducted away from a hot object of temperature TH to
a colder object of temperature Tc, Th for hot temperature, Tc for cold temperature, by a slab of material, and we're going to have cross-sectional area A. So if you look at this diagram right here, this is area A right there. That's cross-sectional area A. And here's our slab of material. What letter here is representing the thickness of this slab? L, yes. So it's, you could call it the length L, but that is the same thing as what they're saying up here in the objective is thickness. And also another thing that's called the thermal conductivity. We use the letter K for that. It's another constant that we use K for, unfortunately.
The thermal conductivity constant, or K, is greater if the material can carry away thermal energy faster. Thermal conductivity K is measured in the units joules per second meter degree Celsius. K depends on the material. K is higher for good conductors of thermal energy like metals, and K is lower for good insulators like styrofoam, air, or wood. Here's a simulation of a high thermal conductivity substance on the top and a low thermal conductivity substance on the bottom. Notice that the thermal energy, i.e. the kinetic energy of molecules, moves faster through the high thermal conductivity substance and slower through the low thermal conductivity substance. Now we can develop an expression for the heat transfer rate by conduction. It depends on the temperature difference between the two ends of the slab, the cross-sectional area of the slab, the length of the slab, and as we've seen, on the thermal conductivity K of the slab.
I will tell you this, that
H is a fraction.
So in other words, how quickly thermal energy is transferred depends on how will this K factor affect it. I'll give you a hint. Will K go on top or the bottom of this fraction? Thumb up for top, thumb down for bottom. K is going to be right on top there. It's a lowercase k. That is on top. The higher the thermal conductivity constant, the faster energy will transfer. How about this? See this area right here, A, this area right here. So that's the cross-sectional area. Think about it in terms of molecules colliding. If I increase the area, will there be more molecule collisions, like an interface between these two objects, or will there be less? There will be more. There's more space for those molecules to hit each other. It'd be like, which will give me a better conductivity, just touching them like that, or touching so they have a big area in contact, like much more area. More area. So you tell me, where does cross-sectional area go on this fraction? Thumb up for top, thumb down for bottom. Yes, it goes on the top. So you see how we can reconstruct this just by making sure it makes sense. Now, how about the length of this thing, otherwise also called the thickness of the slab? They mean this length, L, from there to there. If it's a longer tube that the energy's got to flow through, will that make it flow faster or slower? So let's think about that. So where does L, the length of this thing, go in this equation? Thumb up for top, thumb down for bottom. Where was the length of the, or what they call the thickness of the slab go? It goes on the bottom. And there's only one other thing that we have to do, and that is the temperature difference. Temperature difference is just like voltage difference or pressure difference. If you have a higher temperature difference, or if you have a higher pressure difference or a higher voltage difference, does that make, for pressure difference, does that make air flow faster or slower? Would a higher voltage difference make electrons flow faster or slower? So the question is, would a higher temperature difference make thermal energy flow faster or slower? Where does T go, or delta T, I should say, on this fraction? In other words, a big temperature difference is just like a big pressure difference. It goes here. So this is delta T right here, but actually let's put it as T hot minus T cold, because that'll always give us a positive number. So this is the rate of heat transfer. To speed up the rate of thermal energy flow, use a material of greater blank. The material, only one of these things can apply to the material. For example, when I look up steel, it doesn't say, oh, steel is 3 square meters. Thermal conductivity, okay? Thermal conductivity, and that is little k, conductivity. Blanker slab cross-sectional area. If we want to speed up the thermal energy flow, greater slab cross-sectional area. How about what will we do with the temperature difference? Greater temperature difference. And what will we do with the length or thickness of the slab? Smaller length or thickness. Cool. All right, now in some textbooks, the letter H is replaced by the letter capital P for power, because it is also a rate of energy transfer.